Good day to you. Today we're going to be talking about momentum. Isaac Newton, when he was formulating his laws of motion, tried to reduce matter and motion to its bare bones. Prior to Newton, one of the principles was that matter moved because it had some desire to move. And what Newton did was to try to strip the science of matter and motion of all these kinds of vague and unquantifiable generalities, and to try to reduce matter and motion to its bare bones. One of the quantities that Newton developed to be able to describe matter and motion is a quantity called momentum, which he described as a quantity of motion. And Newton formulated an equation that helped him describe what momentum is. And let's just write that out here. For various reasons, Newton described momentum with the symbol P. And the equation that lets you calculate P is a very simple one. You just take the product of the mass, which we define as m, times the velocity, which we define as v. Now, before we move on, let's take a moment to look at the units of this, because that'll be very important in our subsequent analysis. The units of mass, of course, are kilograms, and the units of velocity, of course, are meters per second, or meters per second raised to the -1 power. And so momentum is simply the product of mass times velocity. Now, there are a number of important things about this quantity. First of all is that momentum has a direction to it. This is implied in the quantity of velocity. Let's remember that velocity is not just speed, it's a combination of speed and direction. So if we have a particle, for example, and that particle has a certain mass, and it's moving in a particular direction, that's going to have a velocity, which we can symbolize with an arrow, a vector. If we take another mass, just the same kind of thing, with a particular mass, and we have it going in a different direction, then that mass is going to have a different momentum than this mass will have a different momentum from this mass over here, primarily because the two have directions. They have different directions. And this will be very important when we start talking about how momentum relates to pressure and energy and those sorts of things. One of Newton's laws is a definition of force, and this, of course, is the relationship that we've seen already. Force is equal to a mass times an acceleration. And let's take another look again at the units here. This is a mass in kilograms, and what we're talking about with acceleration is actually a change of velocity. That is a change of the speed over time. Now, we remember, let's recollect, that a change of velocity will bring about a change of momentum. The reason for that is quite simple. You have a mass in motion, and you have a velocity at point 1 before you applied the force, and then you have another mass after a short time that you've applied the force. That's v2. And so what we're going to see here, the mass doesn't change, and we're going to have an equation that's going to be mass times the change of velocity is equal to momentum. Now, if we work out the units, we'll see that a change of momentum is actually a change of force. And this is a fundamentally important feature of Newton's laws of matter and motion. If you have a body either at rest or in motion, it has a constant momentum. The only way you can change that is to apply a force over a period of time. And the way that that will be manifest is in a change of velocity of a mass. Therefore, force is not only just a mass under acceleration, it's also a change of momentum. Well, that's all for now, and we will see you in another video.